Welcome back. The first speaker is Leah from University of Colorado, and she's going to tell us about that topic.
Yes. All right, so the microphone's working and everything? Yeah? Okay, great. So what I'm going to tell you about today is a project that I came up with on my own, and I was pursuing without really a lot of guidance last year after I graduated with my bachelor's degree. So I'm really looking forward to your feedback, and I'm kind of trying to figure out if there's a fatal flaw or anything. So ask me lots of questions. Just a bit more? Like that? Is that better? Above the button? Oh, whoa, okay.
Thank you.
Now I can hear myself, I think. How's that? That's better? Okay. All right. So I'm going to be talking about the dependence of the non-helical dynamo on shear. So just a little bit of context. I'm talking about accretion disk dynamos here. So we already heard a lot about these from a variety of talks so far. And ooh, I'm going to move this. Yeah. So basically, the MRI generates turbulence, and we need some sort of mechanism to go from small-scale fields to large-scale fields, and that's the role of the dynamo mechanism. So there are a lot of different types of dynamo mechanisms that we could focus on. If you have a density gradient, then in the stratified system, a lot of people know about the alpha effect. It's a pretty common in a lot of different systems. But if you don't have a density gradient, you have this added reflectional symmetry. And so the alpha effect can't work. And there are basically two main alternatives to the alpha effect, like for dynamo generation in the unstratified case. And that's the incoherent alpha effect, which is basically fluctuations about 0 in this same alpha parameter, which I'll explain a little bit more later on. And then also the magnetic shear current effect, which we heard about from Amitabha in the very first talk. And that's basically an off-diagonal resistivity. And when the sign is negative, then that's when this mechanism is active. So a couple of distinguishing features of the dynamo. Basically, if you separate into the mean field and fluctuations, you need more energy in the mean field. And there's also this butterfly diagram, which we've also seen, that I will talk about more. So what I'm going to be doing is looking at this very easy knob to tweak, which is the shearing parameter. So that's defined up here. Yeah, you can see it. But basically, it's how the rotation depends, how it changes as a function of radius. So that definition up there. So what my goal is to see what is the influence of shear on these unstratified systems, and can we somehow disentangle these two dynamo mechanisms or find like a regime where one is active and another is not, and stuff like that. So my tools for this are going to be the shearing box. So Amitabha showed this picture of like the global accretion disk, and then you take a tiny section of it in a Cartesian box so you can neglect curvature effects. And then if you assume that your height of the box is small enough that you can neglect the density gradient, then you get into these unstratified systems, which is what I'm talking about. So I'm using the code Athena, and my shearing boxes will have 0 net flux. And I was trying to avoid this whole mess with Prandtl numbers, so I chose an ideal system. We'll see. Not really sure if I managed to accomplish that. And then I have my resolution here. And then an important thing to note is my box size. So if I have a size of 1 in the radial direction, the x direction, then my box is 4 times bigger in the vertical direction. And this is important because it relates back to previous studies. So people have looked before, especially at stratified systems, because that's the more realistic setup. And but since I'm trying to isolate these two unstratified dynamo mechanisms, I don't look at the stratified density gradient thing. So in stratified systems, some people have found hints of maybe some sort of dynamo cutoff at a critical shearing parameter, and I'm going to come back to that. But in unstratified, people looking at unstratified systems, a lot have used small boxes in the past. So a vertical height that's only, that's the same size as the length in the radial direction. And that's important because there was a paper in 2016 by Stone and Huang saying basically if your box size is too short in the vertical direction, then maybe you're cutting off the dynamo somehow. And so that's really kind of what got me started on this. So I was looking at, so this is illustrated in this figure here. So up at the top, there's a tall box, so it has a height of 4. And in the middle is a short box with a height 1. And the reason they look the same height-wise is because I've just copied and pasted the middle one 4 times so that it has the same, it looks the same. And the point of doing this here is that you can really see, okay, in this small box, the magnetic field is like really wiggly and stuff, but in the tall box, the magnetic field, this is a plot of azimuthal magnetic field. And so in this tall plot, the magnetic field is really coherent on scales of 1, which is the length in the radial direction. And so that is a characteristic of a dynamo. And this is also the unstratified equivalent of the butterfly diagram. So the switching of the azimuthal magnetic field from positive to negative, and on and on. Yeah, so I'll talk more about the period of that a little bit later. But what Stone and Huang did was looking at, for this shearing parameter of 1.5 right here, if you have a taller box, which is in blue, then your magnetic energy, this is the ratio of your mean magnetic energy to turbulent magnetic energy, for tall boxes in blue is much higher than for boxes in green down here, which have a height of only 1. And so this is just kind of a preview because you can see as a function of shear, I get this weird jump. And this is what I'm trying to explain. So I was thinking that I should probably reproduce some of the scalings that people normally do when they do this kind of work, just to see if I'm on the right track first. So these are some traditional scalings that people find. Maxwell to Reynolds stress ratio, which was shown in Pesachon-Psaltis to be 4 minus Q over Q. And I find very good agreement with that for tall boxes and short boxes. I also find a constant kinetic and Reynolds stress to kinetic energy ratio and Maxwell stress to magnetic energy ratio. And then also this constant turbulent alpha, which was defined in a different paper. But I don't manage to reproduce some of the other scalings, which we've seen this plot in the first talk today by Eric Blackman. I just reproduced as a function of shearing parameter what the total stress would be. And so the dotted line up here is the Shakura-Sunyaev fit, and the black points are my data, and all the other colored lines are various people trying to come up with a theory for how to fit this total stress. And basically the point here is it doesn't really have, it's not really well explained. So the thought was that maybe this jump here, so it's only happening in tall boxes. When I do short boxes, I get much better agreement with this. I recover the scaling found in Abramowitz and all. So I was thinking, well, okay, with the Stone and Huang paper, suggesting that the dynamo only functions in tall boxes, maybe the dynamo is getting cut off at lower shears. So to test that, I was looking at the dynamo coefficients. And, oh, that's not very good resolution. But these are the mean field equations, which we've already seen. And basically, if you take the induced EMF and expand in the mean field, then this is the alpha parameter. That's what leads to the alpha effect. And fluctuations in that lead to the incoherent alpha effect. And then this term here is if you have this certain off-diagonal component less than 0, then that's the magnetic shear current effect, basically. So the way I find these coefficients is by the projection method, which was outlined in these 2 papers. Basically, It's basically a least square sort of a thing, but the way I do it is additionally constrained, so it sets some of these, so like the diagonal components of this matrix equal to each other, and it neglects the other off-diagonal components and the alpha yx components. And it also considers only the largest two filtered modes of the magnetic field. So there are potentially some problems with that, and it's been recommended that maybe I check out the test field method. That might give more accurate results. But what I'm doing within the framework of this projection method, what I find, this is the negative of the eta yx parameter. So more positive on more up is more negative. And these all these lines, the blue is the height is 4, and then the green are all height is 1 at varying resolutions. And you can see that I get this same sort of a jump here, which is kind of suggesting to me that the magnetic shear current effect could be here. So I'm finding negative values of this coefficient. And so what my ultimate goal was to try to compare these two dynamo mechanisms. This is still a work in progress, but basically for the magnetic shear current effect, some good positives are that the alpha coefficients average to 0. That's what we would expect. And that the eta yx is negative for all the shearing parameters and all time. So another thing that you can do to check to try to determine which mechanism is acting is by looking at the growth rate of the dynamo. And I attempted to do this. It was actually somewhat difficult, so I have a more limited range of shearing parameters here. But basically, the magnetic shear current effect, the dynamo growth rate should scale with the shearing parameter squared. And for the stochastic alpha effect, it should be linear in Q. So I fit all my growth rates, and both of them were pretty consistent with both the linear and quadratic scaling with Q, so I couldn't rule out either of the dynamo mechanisms based on that. A test of the stochastic alpha effect, though, was basically if you double the volume, then your fluctuations averaged over the volume should halve, and that should mean that your growth rate also halves. So I did one run where I doubled the radial size, and that was to see, like, okay, double the radial size, does my growth rate halve? And that's this run down here, and you can see that it doesn't halve directly, but it does drop pretty substantially. So that's what basically both mechanisms are present here, is what I get from that. And then another thing, so this butterfly diagram here, the magnetic shear current effects can't actually explain where these cycles come from. If you have a stratified system, then you have a very good scaling with Q that's inversely proportional to Q based off of the alpha omega dynamo. But when it's unstratified, there isn't a theoretical scaling yet. So I just decided to see what kind of scaling I would get as a function of shear. So that's what I did up here. The blue points are what I have measured, and the orange squares are the what you would get, the prediction for the alpha omega dynamo, which isn't actually terrible, but if I do an actual power law fit, then I find an index of negative 0.75, so not quite fully inversely proportional. Yeah. So I'm going to be a little bit short, but I figure that's okay. There are a lot of things that I still need to do because, like I said, this is a work in progress. But for instance, like figuring out what would happen if I didn't have rotation, so if it was just plain shear. And then also there's some subtleties with the averaging in the way that I find the dynamo coefficients, and is it actually real, or is it just me averaging over the saturated state of the dynamo? And then just like if I had taller boxes, then the switching would become clearer, so everything would probably be easier to disentangle. Yeah.
We have plenty of time for questions. Okay.
Thank you very much for the very nice talk. I think it was quite convincing that you showed that it's the eta xy, which depends on Q. And then you said alpha is averaging to 0. Did you check also alpha squared? Because it might still be that you have plus and minus alpha, which are making the butterfly diagram. Did you check the dependence of alpha squared on Q? Might there be something here, or?
No, I did not. I know that one way to check if it's being driven by the incoherent alpha effect is to take the coefficients that I measured and just solve the equations using those coefficients. And if you set alpha equal to 0, then that would say that there are like no fluctuations, so there's no possibility of being driven by the incoherent alpha effect. And so if that varies substantially from the from what I actually get, then that could be an indication that there's the incoherent alpha effect. But I haven't actually looked at that, no.
Okay, thank you.
Could you go back to like your second slide?
Yeah.
Ah, that was good. Yeah, there you go.
It's lagging, sorry.
Okay, this is not my topic, but I was just curious. When you run the simulation, when it jumps from the low curve to the higher one, can you design a simulation where it does it half and half? Let's say it's oscillatory between those two regimes?
Well, so these are all different simulations.
Yep.
Yeah.
But let's say you picked one at 1.25.
Right, so I did a sequence from 1.1 to 1. This starts at about Q is 1.2. So I looked at Q as 1.18, 1.15, and 1.11. And it's a little bit smoother, but it never oscillates.
Okay, so let's say you started the simulation then at 1.4. And you gradually lowered the shearing parameter. Does it trace out that same curve, or is there a hysteresis in it? Does it jump down to the lower branch at some other value of the shearing parameter?
So all of my simulations have a constant Q, and I never actually varied the Q.
I'm saying, suppose you did.
Well, in that case, I don't know, but...
Yeah. I was just trying to understand what those two states
are. Right. Well, because, I mean, if there is some sort of hysteresis, then that would be like... So my hypothesis is that the dynamo is like switching on or off. So it would be interesting to find, like, if you brought the shearing parameter down or brought it back up, is the critical shear different or not?
Yeah. Oh, okay. Go ahead, Axel.
Am I right that the incoherent alpha shear dynamo should actually scale, the growth rate of it should scale with the shear to the 2/3 power?
I thought the maximum growth rate should
Maybe
be
that was the maximum growth rate, yeah. Did you confirm such a thing?
that the maximum growth rate is?
That it scales with the shear to the 2/3 power?
The 2/3 I didn't do, but I just did the to the Q.
Yeah. Okay, and can you explain the Q² dependence? Where did that come from? I missed that.
That's from the dispersion relation of the magnetic shear current effects. If you do the growth rate part, then it's
was that in one of the Amitabha papers or something, or where do I find that?
It's in Square and Bhattacharjee 2016, I think.
Which
2016.
One?
Square and Bhattacharjee 2016.
Aha, right. Yeah, right. 2015. Okay, thank you.
There we go.
Okay. I was just going to say, you mentioned the averaging. It might be interesting. So this is averaged in the horizontal planes and then functions of z.
Right.
It might be interesting to try the other plane, average in the zy and see what the function of x, just to see the. I mean, that's also a mean field. So
there's also a mean field.
I mean, so you pick up, you're averaging in x and y and then leaving the mean as a function of z. You can also do the orthogonal averages to calculate mean fields in the other direction.
Okay,
Which would be interesting.
Are there predictions that I could compare to for that?
Well, you could see whether or not, you know, if there's a large-scale field in that case, you could use the same predictions. I mean, the equations are, well, we can talk about that.
Okay.
Yeah. But,
There was a question. Oh, here we go.
So the dispersion that you mentioned in Squire's paper also has a dependence on KZ. I was wondering if you've tried comparing your growth rates to that, since like the dispersion has like a balance between the shear current effect and then diffusion. And so maybe when you're increasing your box size KZ, you're allowing yourself.
Wait, KZ is the box size, or
sorry, the length of the height of your box. As you increase it, you're able to have lower wave numbers in the z direction, and so that could allow you to have maybe a positive growth rate. I don't know if you've checked.
I see. Okay. Yeah, I haven't checked that.
Well, we can talk about it after.
Okay.
You used a toroidal length of the box, which was also 4 times bigger than the radial size. Did you change that, and did you find that that was important?
I didn't change the azimuthal direction
But
at
you
all.
think it's important, perhaps, right?
I mean, it would be important for the incoherent alpha effects because of the volume. That would change the magnitude of the fluctuations averaged.
Okay, but not for the eta2 shear current effect, you think? Or what do you think?
I don't know off the top of my head, but I don't think so.
Okay, thank you.
Another comment or two? We still have a couple minutes. So, hey, sorry, I should have been looking.
The MRI dynamo being a subcritical dynamo, one would expect to have a dependency of the like the eta tensor on the mean field strength. So in 2008 with Gordon Ogilvy, we derived predictions for this tensor as a result of quasi-linear theory of non-axisymmetric MRI modes, and we find that the sign of this diagonal term depends on the strength of the field. So I was wondering if you have tested this sort of thing, and or if not, if it was possible to check whether or not there was a dependency on eta yx on the field strength.
Yeah, so I looked at that model a little bit, but since my eta yx doesn't change sign at all, then there's like when your average magnetic field hits a certain strength, it doesn't matter for the eta yx sign at all. So I didn't find any dependence on it. So.
Questions are great. We still have a moment. It's not a PhD exam. It can be friendly.
I mean, I'm all down for more coffee time.
My question is, you've restricted yourself to a shear box, given the sensitivity of both the dynamo effect itself on height, box height. It leads me to ask, what would the effective curvature be? Do you have any sense?
No. I think there's somebody's maybe looked at it in the global sense, but I haven't looked at it at all. Yeah.
Anything else? Let's thank Leah again. Okay, so I got one in my hand. Oh, you're good.
Prepared. You hit two good. I guess
maybe just a little higher there.
I speak loudly.
Oh, very good. Find a convenient pocket.
Okay. I usually skip them altogether.
there's a pointer.
Yeah.
Oh,
That's
you
good.
might have to do it again, just to.
It's not recognizing it. You hit 2?
It's 2.
Wait, oh, wait, there it goes. Wait a second.
Hey, excellent.
Voila.
Thank you.
So do we start 4 minutes early or tell some pre-talk jokes?
An extra 4 minutes.
So I guess to start with, I want to thank the organizers for allowing me to give a talk and thank the local organizers and friends and colleagues for living in such a beautiful place. Always enjoy visiting Boulder. Got some good friends, excellent hikes. So what I'm going to tell you about today is observations done in the laboratory and reflections on what we've seen in liquid metal flows associated with experiments trying to understand some aspects of natural liquid metal flows. And while there are goals that we've sought in doing these experiments, the approach is much more of going to these sets of parameters and just trying to be a naive observer to see what actually occurs. So we end up seeing many things that we didn't expect or many things that we didn't plan to see. So a lot of the current work that I'm going to show you is being done by the 2 graduate students, Ruben Rojas and Arthur Preveloff, who are here. Till Zerner was a guest that actually helped with the current set of experiments. The experiment, the large experiment, was originally designed and built and operated by Santiago Triana, who's here, and Dan Zimmerman, who's in Brooklyn. In any case, I want to give them credit for that. And I guess this was the group from last summer, so just we usually have undergrads and grad students and various carry-ons on. So I'll talk about the waves we've seen, talk about some of the different turbulent states, talk about dynamo action and the omega effect sum, and then also talk about the explorations that we've been doing to try to understand whether or not one can predict MHD states just from observational data. So we've had a sequence of experiments that started small, 20 centimeters, and become progressively larger with progressively higher input powers, all really trying to model natural flows such as that occur in the Earth's core. You know, you can't actually build a detailed one-to-one model of the Earth's core in a laboratory, failing radial inward gravity, for instance. And there's a longer list than that, but we try to match as many things as is practicable. Geometry, the dimensionless groups that we can match, we do. We don't match them all, and I'll talk a little bit about that. So the current rendition is a 3-meter diameter model pattern on the outer core. So we model the inner core, a deep liquid metal ocean. We don't try to model the mantle or the crust at all, although I do worry about volcanoes. We tend to avoid those as well. So the dimensionless groups available then that we've heard about are Reynolds number that characterizes the nonlinearity of the momentum equation, large Reynolds number being increased turbulence, and magnetic Reynolds number then is associated with the balance between the stretching of magnetic field lines, as is balanced by resistivity that tries to kill dynamos. So various things labeled on here. So a high Reynolds number then tends to be where laboratory experiments often occur in liquid metals since they're low viscosity. We always end up there. Because of the particular ratio of diffusivities, the liquid metal experiments tend to be in about a similar range to planets overall in turbulent conditions, but at modest magnetic Reynolds numbers. Plasma experiments then tend to have perhaps less turbulence, but perhaps larger magnetic Reynolds number. Simulations tend to be slaved, as we've heard many times, around a magnetic Reynolds number near 1, and so then they'll be along the diagonal here, but limited by computational, the computational availability to date. So we're far from the sun, closer to planets. Lots of realistic turbulence, perhaps not quite a large enough magnetic Reynolds number, but we'll see what things look like. Now, this is a diagram from a article by Sanchez in 2014, which nicely illustrates a phenomena that we try to understand, which is dynamo action. So the induction equation governs the magnetic fields for us, and really then just says that we have advection and stretching of magnetic field by the velocity field. We have diffusivity due to electrical resistance, and the battle of these two then tells us whether or not we can get above threshold for dynamo action, which we are currently subthreshold. We have amplification of the magnetic field without self-exciting dynamos, and what we see actually is associated with alpha and omega effect we've heard much about. We have very strong omega effects in our experiment. Amplification then of, let's say, poloidal magnetic fields getting wrapped up by differential rotation, seeing very strong azimuthal magnetic fields. we do see some evidence then for the regeneration of poloidal magnetic fields from azimuthal magnetic fields, but that is weaker and perhaps too weak in our current setup and something that we ponder overall. So actually there have been a number of experiments that have been conducted or are currently being conducted, almost all using liquid sodium to try to understand these things. And we heard about the Dresden experiment that is nearing then operation doing precessional work. We have successful dynamos in Karlsruhe and Riga, although in geometries that were very tightly specified to have kinematic dynamo velocity fields. So they did what they were designed to do, but very far from natural geometries and natural saturation mechanisms that we might expect to occur in planets. Of course, our talented team in Cadarache had their French blender that had many interesting dynamo states, including interesting reversal polarity states, but only with ferromagnetic impellers and many internal arguments among themselves as why ferromagnets. Obviously, we don't expect ferromagnets to play a dominant role in planetary cores since they're too hot, way above the Curie temperature. There's just no ferromagnetism deeper than a planet. All we have are conducting liquids. Hi, Carrie. So Carrie's done liquid metal and also plasma experiments in Wisconsin. And then I have a long-standing collaboration with the team in Grenoble. So they nickname our experiment Big Sister, and so I guess theirs is Little Sister. And so we exchange ideas and diagnostics, and Claude Nataf and I speak frequently. So we'll be talking about then the Maryland experiment, which is now in its 4th rendition at 3 meters in diameter. So the experimental setup then briefly has a 3-meter diameter outer sphere which rotates up to 4 revolutions per second. All good planets rotate, and we want Coriolis effects to be important, if not dominant. We have a 1-meter diameter inner core model, if you will, that rotates up to 15 hertz, but with a really nasty resonance at 9 hertz that you have to jump over if you don't want the whole experiment to vibrate really madly. 12.5 tons of liquid sodium then form a deep liquid metal ocean, which is our model of the outer core. We can apply external applied magnetic fields to look for gain, which we need to since we see gain but no dynamo action. We measure 31 Hall probe locations on the outer sphere to look at the spatial and temporal dynamics then of the magnetic field. We have dynamic pressure probes at the top, looking at that. Static pressure probe as a diagnostic, and thermometry as diagnostics. And then 2 Hall probes that are actually down inside the liquid metal. And you know, the thing about an experiment like this, unlike a planet, is that we're very close to the source of the induction. And so you can measure then higher frequency turbulent fluctuations in a way that are screened for the Earth's magnetic fields by the screening of the mantle. And then torque sensors, one of the main diagnostics we have. So this is spherical Quet flow. We rotate the inner and outer spheres at different velocities to get high magnetic Reynolds numbers, and the torque it takes to drive the inner sphere allows us then to know the amount of power going in, and is a critical diagnostic for understanding the state overall. So the Reynolds number for this experiment is up to about 90 million. So we're far beyond what can be simulated in ab initio calculations, clearly, which can go to maybe tens of thousands these days. The magnetic Reynolds then is up to around 900, so it's Earth-like in character, which was one of the design purposes of the experiment, was to approach the magnetic Reynolds number of the Earth. Ekman numbers down to 4 times 10 to the minus 8, so we are rotationally dominant in many ways that we observe. It turns out that the Rossby number, the differential rotation between the inner and outer sphere relative to the outer sphere rotation rate, is really the primary parameter that determines the state. So if you go to the same Rossby number but different Ekman numbers, you tend to see the same state. So you can vary Ekman number and you'll just see scalings in amplitude but not character of, let's say, the waves or otherwise that we'll look at. So obviously we expect that the Earth's outer core is undergoing compositional convection as the main driving mechanism. So we didn't do convection in this experiment, although we've done convection experiments in liquid sodium, specifically because it's very difficult to get the high magnetic Reynolds number in a sodium experiment doing convection. So at the same scale, the same power levels, we would be challenged to get the magnetic Reynolds number of a few, whereas if I differentially rotate instead and use angular momentum as my buoyant quantity, if you will, we can get to magnetic Reynolds numbers that are closer to the Earth. So this is one of the ways it's not exactly Earth-like, but allows us to have much more significant induction. And I guess I wrote down the equations of motion because I like them. I don't really have anything more to say. I like nonlinear partial differential equations, which is maybe a feature for an experimentalist doing this sort of work. So, okay, wide angle shot of the 3-meter experiment. So it's a real device, probably about 20 tons of stainless steel and 12.5 tons of sodium. So So in part, this experiment was designed intentionally to be one of the world's most expensive fishing lures for theorists doing numerics. I do like to fish, and this has successfully netted then a number of friends and colleagues to simulate spherical Quet flow to look at the various states and dynamo action. And I want to highlight a recent paper Santiago was a co-author on, and the work of Johannes Wicht, but also I'll come back to this Fink and Tilgner paper suggesting that a roughened inner sphere may be advantageous to dynamo action, which has launched us on, I guess, what I'll call the Fink saga, which is the current episode in our experiments. So what do we measure? So these are time series then of the sorts of things that we observe in the experiment. So we have external magnetic fields here at 2 places, but actually at 30 places. And so I'm not going to show you 30 time traces, which is a little confusing to look at. This is in a particular state where it's bistable between 2 states, which is in a certain range of Rossby number. The torque it takes to drive the inner sphere then in this case actually shows large deviations between this bistable state. We have these 2 internal magnetic fields, one measuring the azimuthal magnetic field at one location and the other radial magnetic field in a finger down into the sodium. And then the dynamic pressure probes, which show extremely large fluctuations associated with the vortices and zonal winds, and otherwise, which are modestly hard to interpret. So here's just kind of a status checklist where we've been and where we are, where we're going. So we did about 850 hours of experiments in water initially. Thought to start with, this is just going to be a diagnostic shakedown of the experiment to make sure everything was working fine before we did sodium. But it turned out many interesting things to see in water, so we lingered there for a while. And Santiago and Dan Zimmerman's dissertation was actually substantially on the water data and states. We've run about 400 hours of sodium experiments. We managed to achieve full speed on the outer sphere in 2015, although that was a bit complicated getting all the way to that speed mechanically. There's a longer story, which I won't bore you with. Currently, we've had a bearing failure of the shaft that holds the inner sphere in place, and so the inner and outer spheres are currently locked in place, pending us draining it and fixing that bearing then, which is in the plans. So scientifically, we've seen precessional states, inertial waves, which I'll show you, bistable states, 12 plus different non-dynamo states, depending on Rossby number in particular. The power varies strongly with Rossby number, significant local magnetic field amplification and global magnetic field amplification of dipole or quadrupole magnetic fields, which I won't detail because of time constraints. So we're really focusing right now on designing and implementing a roughened inner sphere based on the Fink saga, and also prediction studies of how do we take experimental data and test our ability to test or predict magnetic field variation at 90 million Reynolds numbers. So the first thing I want to tell you about are the precessional observations we did. So it turns out that in early diagnostics, if you co-rotate the inner and outer sphere and attempt to achieve solid body rotation, you cannot, because we did not align the axis of the experiment with the axis of the Earth in Maryland, and the precessional torque of the Earth is enough to drive and resonantly drive an inertial mode, the spin-over mode, which achieves a modestly high amplitude in the experiment, but gave us a test bed for looking at precessional states. And so we didn't design it to study precession, but we studied it nonetheless because that's what nature presented us with. A precessional experiment, and obviously this is very geophysically relevant because the Earth's axis also precesses and gives rise to spin-over modes in the Earth's core that have been measured in amplitude by Bruce Buffett. So here, this is a velocimetry, so this is down to the sodium in centimeters, 70 centimeters in, time in seconds up to 120 centimeters. Red would be moving away from the probe, blue off, so this is off axis just looking. So the sodium's doing this in the rotating frame. So in the non-rotating frame, then it's doing this. Santiago, am I getting the dance accurate-ish? Okay, so this is spin over. It's a very weakly damped inertial mode restored by Coriolis forces in the pressure term, and now I'm a little bit dizzy, but that's okay. And so these are simple oscillations then at lower rotation rates. This is the phase of these oscillations as measured with depth. As we go to lower Ekman number, higher rotation rates, we develop more complicated spin-over states on the internal, including a phase wrap that occurs at a certain distance down into the state, which is not surprising if one studies the literature on these things, because the spin-over mode in a spherical annulus has conical shocks, oscillatory shocks, not near a boundary, but on cones. And so we actually can observe these things. So the inertial modes have an unusual dispersion relation that gives rise to ray focusing if you study the ray optics or if you do the numerical problem, then these conical shocks occur. And not just for spinover, but for other modes that may occur. So, okay, so we heard about the Taylor-Proudman theorem. If we take the equations of motion and take the curl and we argue that various terms are small and toss out the time derivative rudely, then you get the Taylor-Proudman theorem that says that there's no velocity variation along the direction of the rotation vector. I regard the Taylor-Proudman theorem somewhere along the lines I regard the Bernoulli theorem, which is that is very occasionally approximately true in simple situations that we probably shouldn't be teaching our freshmen. In the end, if you don't set the time derivative to 0, if you retain that and you take the curl, then you get that the time derivative of the vorticity is given by the z derivatives of the velocity, and that's a wave equation. So the geostrophic modes are just the zero frequency branch of what is a family of waves that occur almost always at sufficiently low Ekman number. So I think that's maybe a slightly more subtle, but not that much more complicated story that we could be teaching. So since these, I believe, occur quite generically in natural flows as well as experimental flows. Okay, so now if we do rotate these spheres independently, we have a zoo of states. So this is labeled then with Rossby number along here. These are the spectra, power spectra of time series of the wall shear stress at one point on the outer sphere. Not that I could go over all of this, but we have broadband turbulence together with waves, which are narrowband in some cases, waves which are broadband in other cases. We transition between different states with different waves, with different azimuthal wave numbers, and I refer you to the 2014 GGR that details those states. At small negative Rossby number, we have very high Q wave states which are observed, which are inertial waves, which are driven by the differential rotation of the spheres. So we can have an inertial wave driven by the precessional torque of the Earth, but we can have inertial waves that are driven by differential rotation. And I believe that actually, in fact, when you have zonal shear in various geophysical situations, you can drive waves if they're of high enough Q. Apparently, shear is a ready way of driving a wide variety of waves. So negative would be in the rotating frame, the inner sphere rotating against the global rotation of the outer sphere. So positive, yeah, retrograde, right. Yeah, so in fact, the high Q inertial waves are always at that retrograde, and they're always anti-symmetric as well. So this details that a little bit more. I think some of this may be actually from the 60 centimeter experiment. So basically, at small negative Rossby number, then you have a variety of inertial modes that are excited by the differential rotation. And I believe Santiago and team have achieved a better understanding of the resonant triads that come into play in exciting these overall. But we were able to correctly identify, in collaboration with Rietord and Tilgner in several papers, that the spatial structure of these modes maps directly onto the spatial structure of the simple linear inertial modes in frequency and spatial structure and otherwise. So they're actually relatively simple structures, although they're living on a background turbulence of Reynolds numbers in the millions. So apparently they're able to survive in such a context. Perhaps much in the same way Rossby waves can survive in high Reynolds number flows in atmospheres, Rossby waves being a special branch of these inertial modes. Now, so I should explain, this is then varying Rossby number. Each line here is a power spectra of a single component wall shear stress. So the power spectra, bright red lines are just sharp peaks in frequency, this being frequency normalized by the outer sphere rotation rate. So if we go to positive Rossby number, then we tend to have more broadband states, although these broadband states have broadband waves that exist in them as well. They're not as clearly identifiable as inertial waves, but there are other waves that are occurring in the background of the turbulence overall. And actually in this particular zone right here is where we have the bistability. So at any of those Rossby numbers, the system will change back and forth between a high torque state and a low torque state with very different dynamics. So it's not a hysteretic state, although it may be in a more viscous domain. It's just two disconnected turbulent patches with improbable routes that you occasionally hit to switch back and forth between them. And I guess we might all hope that the North Atlantic conveyor belt doesn't have two different states like that, but now, so one of the primary diagnostics that experimentalists tend to use when you're determining boundary conditions such as rotation rates is that the hydrodynamics, or the magnetohydrodynamics, actually determines how much power or how much force is required to maintain that state. So that's a primary diagnostic, which is telling you about the state's ability to ingest power or a flux of power through the system. So power is torque times the rotation rate, so torque is the simplest thing to measure for that. And here then is torque at different Rossby numbers relative to the torque at the state with the outer sphere stationary. So we just sort of pick that as our reference state. And so the torque is sensitive to being in these different rotational states, and we switch between these different states, and then there are large changes in the torque. There's a slight negative Rossby number, a peak in the power the system ingests, which I'll come back to, and then these bistability states are here. So this is all then, in some sense, hydrodynamic. If we don't apply large magnetic fields, we see the same thing in water as we see in sodium. But if in sodium then, if we go and we apply external magnetic fields, we can then examine how much gain we have in these states. And you can look at the gain on single probes if you want. For instance, you can look at the gain on the finger down inside the sodium. How much gain do we get when we apply magnetic field on the azimuthal omega effect generated, which are these circles. So all these circles then are ratioed to the external radial field. How much azimuthal field have we generated? And so we get here, let's say, a factor of 7 or 8 stronger azimuthal magnetic fields than we apply in radial magnetic fields. So again, relatively vigorous, not terribly surprising omega effect in the system. So if we measure the induced radial magnetic field relative to the applied radial magnetic field, these are these inverted diamonds here, and they tend to be around 1, sometimes even being suppressed or reversed, except for a particular state near the peak in power ingestion here. So actually we have several peaks in maximum omega effect, and actually a particular small zone around peak power where we have not just amplification in the radial magnetic field of one probe, but actually global amplification of the dipole field, which is not present. If we turn off the external magnetic field, that then scales with the external, although we don't exclude the Earth's magnetic field. And so you can actually observe the Earth's magnetic field obtaining gain from the experiment as well. But all of these magnetic fields are small compared to the saturation magnetic fields you would expect in the system by all the relatively agreed upon and tested estimates of that. So we don't expect any of these states are saturated dynamo states, and we don't expect small-scale dynamos that would occur as well. All right, now, so Fink and Tilgner did numerics where they put a numerical body force near the inner sphere and saw then a reduction in the threshold of dynamo action in magnetic Reynolds number by roughly a factor of 2. So these are both in Fink's doctoral dissertation work and in their PRE from the year earlier. And it's thought then that what this does is increase the poloidal flows in the system, perhaps increase the hemispherical helicity in the system, and definitely increases the equatorial jet coming out from the inner sphere. And so, based on this, then we have set out on a path to implement this. So the thing is, this body force near the inner sphere, which is easy to implement by routine in numerics, is not so easy to implement in stainless steel in the lab, right? We just don't have a body force routine we can install on the inner sphere. So what we do need to do is we need to drain all the sodium out into a storage vessel that we've spec'd out, and we need to extract the whole unit, and then we need to apply something onto the inner sphere to make it rough, and reinstall and refill and run and see what happens. So there's no guarantee what we're going to see because the numerics are done at Reynolds numbers, again, of a few thousand, where our Reynolds numbers are at 90 million. So we have comparable magnetic Reynolds numbers to the simulations, but not Reynolds numbers. So, so having talked then to Tilgner and Underklad-Nataf and other colleagues and debated various ideas for the inner sphere, we've been exploring then having some criteria. What do we do to the inner sphere? So for instance, some criteria which seem sensible is I want whatever I do to my inner sphere to be mechanically secure at full speed and full torque so that whatever I put in there doesn't come loose. I'm going to put that as the first criteria if you don't mind. So we want to approximate then something like 5% of the gap in radius near the inner sphere. We would like to increase poloidal flow and helicity. We would like to increase the amount of power being ingested in the system, but perhaps not more than a factor of 2. There are practical issues of how many hundreds of kilowatts we're actually prepared to both apply and extract as heat. We'd like them to be compatible with the various M-fold waves that we already excite, M = 2, 3, and 4. I think we should very carefully break the symmetries of the inner sphere of the experiment as a whole. The states we see obviously understand the symmetries of the underlying system, and I miss Edgar Knobloch. He should be here this week. Oh, well, we'll see Edgar sometime. But in particular, I think preserving point inversion symmetry and reflection symmetry so that B and minus B are both allowed solutions then makes it more likely that dynamo states would explore both B and minus B intermittently, which would be a feature that would be reasonably positive. Also, I would intend to break the phi to minus phi symmetry, perhaps with a chevron-based design, so that if I reverse both rotation rates, I get a different set of states. So we basically double the number of available states by breaking that symmetry. So at least that's the current plan. So what we've done then is done model studies with baffles like this or baffles like this, and measured the power it takes as a function of Reynolds number for various radial extent baffles. And then for the chevron-shaped, whether you go wedge or scoop in your rotation direction actually gives you a different state and a different torque. So Ruben Rojas has been measuring that out in great detail. To a certain extent, also doing velocimetry to look at the equatorial jet strength. So as the torque here as a function of Rossby number is extremely sensitive to modifications of the inner sphere, where the peak power end actually tends to move and the amplitude of the peak power is also adjusted. So these are black is smooth, and then we have 10% straight and scoop and wedge, 10%, and then 5% scoop and wedge. So it seems likely that 5% chevrons, 12 baffles is the current favorite design. Yeah, well, and it is. It's a pump, if you will. So I should say all of these measurements have been done in a 40-centimeter water experiment with 3D printed inner spheres with the baffles on them, since that's a practical notion. Okay, let me talk for the last few minutes then about MHD prediction. So many of my senior theory colleagues in nonlinear dynamics have all taken to doing prediction studies of various sorts on nonlinear systems. So the basic idea then is, can we do prediction, let's say, on the Earth's magnetic field? It's a controversial proposition. We do not have a predictive science of geomagnetism, okay? So the idea is we can have data from the experiment then, that we have observed data, and can we then observe data from some set of experimental time series, and then retaining some segment that we don't train on, can we then able to predict off the end of that? And, you know, we had exercises done by our theory colleagues on weakly turbulent systems that work surprisingly well, which I'll show you briefly. So we decided to try it on the experiment. So the basic notion then is they implemented, and this is Brian Hunt and Ed Ott and J.D. Pucks, the graduate student, you observe a vector of observations from your turbulent system or your weakly chaotic system. You then observe the output state of a reservoir computer and compute an output vector which most closely allows you to predict the next time step. So you're basically training a tool by observing data to do time stepping for you. If you successfully trained just by observing your data, not knowing anything about the system, to be able to time step, then at t equals 0, you can just close the loop and now just give your predicted time step back into the thing. And now you have a system that is in principle capable of mimicking your external system off the end of your time series at t equals 0. Okay, now there's no reason that this should work just by estimating an output vector from least squares to do one step prediction, other than the fact that this output vector can be on the order of 4,000 dimensional, and you are, when you choose that output vector, choosing among a 4,000 dimensional collection of dynamical systems to choose the one that most closely mimics your data. So that's a very high dimensional space of dynamical systems, but it's not maybe terribly surprising there's a copy of your system somewhere in that high dimensional space. Okay, so they did it first. It was the reason why we decided to try it on the experiments for Kurimoto-Shidoshinsky weak turbulence data. This is just a one-dimensional PDE that some of you may have played with. It gives you wave turbulence. So they took observations of numerically computed Kurimoto-Shidoshinsky. They then trained on it under some initial set and then predicted on it starting here at t equals 0. This is the observed state they didn't train on. This is the prediction that came out of this tool after observing Kurimoto. This is the difference between those two vector fields. And so for on the order of 5 Lyapunov times, it was able to correctly predict weak turbulence, which surprised us a little bit. Not nearly as surprising as the next figure, which is probably the most surprising thing that I've seen in my entire career studying nonlinear systems. Once they trained this tool to mimic Kuramoto-Sivashinsky, they could then ask the tool what the Lyapunov exponents were. And computing those then, in red here are the Lyapunov exponents from the reservoir computer. In blue are those from the original Kuramoto-Sivashinsky. They were able to match the first 6 positive Lyapunov exponents and did pretty well on the next 10 or so negative Lyapunov exponents. If you told me 10 or 20 years ago this could be done on this high-dimensional dynamical system, I would tell you no, it's never going to be done. But apparently this is able to, now one of the things to observe in this, though, is they're putting in zero-noise, double-precision data into this tool. So they have, right, there's a lot of subtle things that go into the training data that wouldn't be there for naturally occurring data or for experimental data. So talking with Brian Hunt then, we decided we would just try it then on a 33 vector of magnetic field time traces out of the 3-meter system at a Rossby number of -1.7 and full Reynolds number. And so we're training on a 33 vector. Here at time 0, then we start predicting on data that we had not trained on. This is just one component of the 33 vector. It's hard to look at all 33 components. But in fact, for here, the first 10 rotations, it actually does reasonably well at matching the waves in the system, even some of the small-scale turbulence that's advecting along with the system. Brian and I were surprised this worked so well. One of the things I should tell you is that if you try training it and predicting on one component of the magnetic field, it does terribly. So apparently having spatial and temporal data that you train on it is important for getting this to work. And it probably is training somewhat on the advection of structures internally, although we're not specifically asking it to do so. So this is rotations 10 through 110, where it's retained a prediction of the large-scale waves, but has lost the ability to predict the small-scale turbulence somewhat sensibly. And then here at rotations 250 to 270, it still has waves, but they become phase incoherent with the waves in the system. So basically, the prediction has failed at that point. And so we continue looking at various ways of doing this. This is, again, just a direct comparison of one component for, I guess, the first 30 rotations. And then, since I haven't showed you all 33 components, here is then a rendering of the magnetic field of experimental data compared at, I guess, two magnetic dipole timescales, what the prediction is. And so it does a reasonably good job of predicting short-term weather of the magnetic field. Now, can we do this in the Earth? And this will be the last substantive slide. We trained in the experiment on a system with a 3-second magnetic dipole diffusion timescale for 20 magnetic diffusion timescales. So that's how much data we allowed it to observe. So the Earth's magnetic dipole timescale is 30,000 years, but of the high-resolution data we have, high L data for the Earth, we have only about 0.007 T available. So it's quite likely that we just don't have a long enough time record of the Earth's magnetic field to be able to get a tool like this to successfully predict. But you know, this is an open question that we continue to ponder. And I'll just stop there. Go ahead, Father.
Oh, very good.
And you had this fantastic gain of 8, 7, or 8 or so. Could you imagine to infer a little bit the beta effect on the spaces, to take laminar flow on the spaces and then look what could be a beta effect? Is it factor 2 or 3 or 4 or whatever? Is it possible, do you think?
Okay, so one of the things that we would like to model better is the actual structure of our zonal flow using the tools of helioseismology, but we actually don't know how much gain to expect or how much resistivity we might have until we can measure that. Although we spent a fair amount of time motivated by Yuri Tumeray's talks I've heard a number of times, looking at the acoustic modes and measuring zonal flows, which is a goal.
Okay, just a second.
Hi. How does your tool compare with sort of more traditional data simulation techniques? So I realize this question doesn't make sense for a geodynamo problem, but you tested it on simple problems.
In fact, in parallel, Sarah Burnett in my group is actually working on traditional data assimilation tools using a spherical code. We don't yet have it working. And so our hope is to actually compete those techniques. But that takes a lot more work, actually, to modify a 3D MHD code to data assimilation, where this particular reservoir computer is a 30-line MATLAB script.
But what about that simple test you showed at the beginning? That would be simpler, no, to implement?
The prediction tests?
Yeah.
So data simulation is a very definite possibility, and the tools are well known from atmospheric physics. It turns out that that's actually quite a bit of numerical work to put a data simulation wrapper on an MHD code. Years of work.
Okay, I get one first. Dan, the roughness that you added, it was something physical, or was a gee whiz, I wonder what it does kind of thing?
Okay, so Fink and Tilgner added a body force. We cannot do that in experiments, so we're going to add baffles. So we're basically going to add pump-like, relatively small features, but ribbons more or less attached to the inner sphere. But ribbons of the order of the dimensions that they had in their numerics.
Yes, I wanted to know if you saw some coupling of during the sodium experiment, some coupling between the magnetic field and the inertial waves, as you saw in the water experiment. Did you see the inertial waves?
Yeah, so the inertial waves induce magnetic fields. So that coupling we've observed readily. In fact, that's the easiest way to observe the spatial pattern of the inertial waves, is to observe the induced magnetic fields that they produce in reaction to the external magnetic field. I think we've done occasional experiments where if you turn up the magnetic field high enough, you start getting large modifications to the inertial waves. No doubt changing the dispersion relation.
I don't want to stop the questions. They're really fun.
Just coming back to the data assimilation, are you using variational data assimilation or ensemble methods for your data?
For Sarah's work?
Yeah.
Oh my gosh. Okay, so Sarah's being co-advised by Kaio Ide, an atmospheric scientist, and so I would need Kaio standing at my side to answer that question.
You can get
LEPT. Oh gosh, there's some acronyms that I'm not well versed in. Local ensemble, Kalman filters.
Okay, so ensemble.
Yeah.
That was the key word. Okay, thank you.
I need to study more.
Go ahead.
Is there an optimum height of the roughness that is needed to drive the dynamo, you think, or?
So I mean, so there's a lot of theoretical notions that maximizing the helicity for a given amount of kinetic energy is positive, and so then the hemispheric helicity will be a strong function of the size of those. A bigger practical problem is we're already injecting or using about 100 kilowatts of mechanical and electrical power. As you make those baffles wider, that goes up by a factor of 2 or 4 or 10. We're not going to be able to supply a megawatt of mechanical power and extract a megawatt of heat. So that's a bigger practical consideration. Power flux.
That's great. Let's thank Dan again. Michael's visiting us from far away. There's the title of his talk. Go ahead, Michael.
Okay, thank you. It's okay? Yeah. And actually, I'm a lucky guy. I will give you 2 talks. Today, I will talk about my main subject of experiments in ellipsoid and numerical dynamos on inertial instabilities. And tomorrow, I will replace Benjamin Fabier, who could not make it, and I will talk to you about local models and the description of the saturation state and the turbulence related to those instabilities. Okay, so our main motivation for studying inertial instabilities is the dynamics of a planetary core. So as you probably all know, if we go down into the Earth, we will find 3,000 kilometers below a huge ocean of liquid iron, which is called the core. And the core is something that we find in lots of terrestrial planets, and also in moons and in the biggest asteroids. The dynamics of the core is very important because it has an important role on the thermal and dynamical evolution of planets, and also, of course, because the free dynamics in the core is responsible for the magnetic field generation, with various results for various planets. So, for instance, we have a dynamo on Earth today, but we don't on Venus. We have a dynamo on the small moon Ganymede of Jupiter, but we don't have on Mars. So there are different results for planets which sometimes looks close enough. So of course, understanding this is a challenge in planetary science, but it's also a challenge in fluid dynamics because it involves flows with rotation, buoyancy, MHD turbulence at typical scale, which are way beyond our day-to-day experience. So when you talk about core dynamics, the standard model is convection. We have heard about this already several times. And so buoyancy-driven flow in a rapidly rotating spherical shell. And indeed, convection does a great job to explain the present state of the magnetic field on Earth. So, for instance, the dynamo, so I took an old example here, but we have a more advanced model now. The dynamo driven by convection is capable of explaining the mostly dipolar shape of the Earth's magnetic field, and also its reversal, and so on. So, convective dynamo seems to work fine for the Earth's core today. But even for the Earth's core today, there are still lots of open questions. And for instance, because the energy budget is very tiny, and we are not so far away from being super adiabatic, okay? And for instance, these days there are lots of discussion about the thermal conductivity of the core at the core mantle boundary. And the present state is that most people believe that part of the Earth's core is stably stratified, actually. Not all of it is convecting, but only part of it is convecting. Things go worse when you go back in the past, because in the past the buoyancy flux was smaller, and then it's very difficult to explain the old magnetic field of the Earth 3 to 4 billion years ago using convection. And also convective dynamo does not work well for small bodies, like for instance Mercury or Ganymede. So for instance, it's difficult to explain how Ganymede could have still convection in its core today, why it is so small. So it should be dead like the moon, for instance. So it is of interest to study other ways to drive large-scale flows, turbulent flows, and dynamo in planetary cores. So to drive large-scale flows, we need energy, and there is a huge reservoir of energy in planets, which is just rotation. So just to give you a few numbers, if we take the Earth and the rotational energy of the Earth, we find this number. So we have enough energy in the spin of the Earth to sustain the dynamo during up to 63 billion years. So 10 times the age of the Earth. Also, the question is to know how, because if you take a planet which is a perfectly rigid container rotating at a perfectly constant rate, well, the fluid inside will just rotate with a solid body as a solid body rotation, and nothing interesting will happen. Luckily enough, it's not the case for planets, and all the planets the rotation state of planets are perturbed by what we call harmonic or mechanical forcing, including libration, precession, and tides. So precession, you remember, Dan already showed it. So it's the fact that the axis of rotation of the Earth, for instance, is also rotating through time. Libration, it's important for synchronized planets, so for instance moons. It means that the rotational velocity is not constant through time, but it's slightly oscillating. So here you have 1 picture per day of the moon, and you see, we always say that the moon is synchronized on Earth because it spins at the same velocity as it orbits, but it's only true on average, and actually it's also doing that in addition to its rotation rate. And tides, finally, so tides, it corresponds to the fact that about twice a day, the ground is going up and down, and that also takes place at the core mantle boundary. So twice a day, we have a change in shape like this when we rotate with the mantle. All those perturbations in planets are very tiny. So for instance, the amplitude of tides is about 30 centimeters, so it's 10 to the minus 7, the radius of the Earth. So it's very, very tiny perturbation. For the libration, so the amplitude of libration for the moon is about 7 10 to the minus 5, the amplitude of rotation. But you all know, I think, that even tiny perturbation can have large-scale consequences. And to show that,
Jamie Vendera is famous for using the sound of his voice to destroy wine glasses. They seem to simply explode.
Okay? One more time. I don't know where the micro is.
Jamie Vendera is famous for using the sound of his voice to destroy wine glasses. They seem to simply explode.
Okay, so that was just to wake you up. The key point here is that tiny perturbation can have large-scale consequences provided that your periodic perturbation resonates with some vibrational state of your system. We have all that in planets. So as I already told you, we have libration precession tides, which are regular, tiny but regular. And we also have vibrational state in planets, which are the inertial modes. So inertial modes are the eigenmodes of the Euler equation written in the rotating frame of reference. Okay, you have the Coriolis term here. So I show you some of those inertial modes in spheroids here, coming from the analytical solution of Kerswell. And all I will need for this talk today is that inertial modes have a given azimuthal periodicity, which I will note M. They have a given frequency, omega. And this frequency range only between -2 and 2 times the spin, the spin frequency of the planet. Okay, so in planets we have harmonic forcing plus eigenmodes. So can we resonantly excite large-scale flow with this system? So to study that, we have built different experiments. So this one is a libration experiment in SpinLab at UCLA. You have an ellipsoidal container. So ellipsoidal, meaning that the 3 axes are different, oscillating on a rotating platform. So that's a model for libration. This is a precession experiment. You see that the container, which is here, is rotating along an axis which is inclined, and the whole setup is also rotating on a rotating table. And the tidal experiment is here. So it's a sphere which is molded in a silicone cylinder. It's rotating. And then we have those 2 rollers that come and compress from the side, giving an ellipsoidal shape to the container. And those 2 rollers here are also linked to a motor so that we can independently control the rotation rate, the spin of the planet, and the rotation rate of the tidal distortion. Okay, that would be rotation rate, the spin rate would be 1 day on Earth, and the rotation rate of the tidal distortion will be the orbital motion of the moon around the Earth in 27 days. We can independently control those 2 systems. All those experiments have a typical radius of about 10 centimeters, and these are what we see. So let's start with this one. You see, you are in the rotating frame of reference. You see the librational forcing. And first, we excite waves. These waves grow in amplitude. And finally, so first we excite waves. Waves grow in amplitude. And finally, we excite bulk filling turbulence in our system. Same story for the tides. You see first waves here, which grows in amplitude. And then bulk filling turbulence. And again, the same for the precession. I should have said what we see here. So we see the flow in a vertical cross-section. We have a laser sheet. And we have tiny particles that reflect lights in the sheet. So you see basically a zone of strong shear. Okay, so all the work we have been doing actually were initially motivated by the work of Malkus in the 60s. He was the first to suggest those mechanisms as a way to drive dynamo in planetary cores. But at that time, the work of Malkus was completely rejected because people were saying, well, the forcing is small, so the flow is small, so it cannot sustain a dynamo. Again, as I've already said, and as was explicitly written by Kerswell in this paper, so at that time, in Malkus' time, critics focused upon establishing the energetic irrelevance of the laminar response, so the base flow driven by the forcing, rather than considering the instability and the fully turbulent case. When you look into the turbulent case, even a weakly steered core driven by precession, librational tides can have enough energy to sustain a dynamo. Okay, so I've shown you this glass example to show a resonance. But that was a direct resonance, and it's not so easy in our system. If you look closely here, you might see that the frequency of the wave is half the frequency of the forcing. Okay, so it's not a direct resonance, it's actually a parametric resonance. So it would be closer to a swing, because you all know that to swing a swing, we need to crouch in the middle and straighten up in the both extreme positions. So we need to excite the system with twice its eigenfrequency. And again, to show an example, so I didn't find a nice movie of a swing, but I did find this one. Okay, so we are in Santiago de Compostela. You see this object is 54 kilograms. The rope is 21 meters. And here you need 4 monks, and they will do a parametric resonance, okay? So look, so from a very tiny initial excitation, in only a few, I think it's 5 or 6 oscillations, you reach a height of 20 meters and 68 kilometers per hour of the system. It's really amazing. Okay, so parametric resonance, it is an instability. And you can write the maths, and it's exactly what's happening in our fluid system. So let's come back to fluids. I take the example of a libration state. So now we are in the rotating frame of reference, and our system, which is ellipsoidal in the equatorial cross-section, is librating. So the base flow looks like this. So you have a base flow, a direct driving because of the topographic coupling with the ellipsoidal shape. It just has an azimuthal wave number of 2 and a frequency of f, the libration forcing. Then if you write the Navier-Stokes equation in the rotating frame of reference and you try to find the growing perturbation above the base flow, so you write this perturbation as a sum of eigenmodes, then the libration, the nonlinear term between the libration base flow and some mode, let's say I, will generate a forcing term with a azimuthal wave number 2 coming from the base flow plus mi, and a libration and a forcing frequency f plus omega I. So that might force mode A here. So let's say a mode K, which will have resonance frequencies and azimuthal wave number. So we can have this forcing, and then with the other component of the base flow, this forcing, and the two match to make an exponential growth and an inertial instability. We have resonant condition here, and the especially interesting one is this one, because the frequency of the second mode must be equal to f plus the frequency of the first mode. You remember, eigenmodes have frequency between -2 and +2 only, meaning that you can have a libration instability only for a forcing, which is between 0 and 4. But so here are different examples in the experiment. We keep the same Ekman numbers, the same tank, the same container. We just change the forcing frequency. This one is the one I showed you already. It's a forcing frequency of 4, meaning that we are just at the edge of the resonance domain. So we couple waves which are horizontal like this. But other resonances are possible with various shapes like this. So in here we have all the experiments done by Alex Granam, which was a great PhD student, changing the forcing frequency, the frequency and the amplitude of the forcing. The blue points are unstable, the red points are stable. So we have various resonances up to a forcing frequency of about 4. It goes slightly above because 4 is valid in the limit of small ellipticity of our container. And it's not exactly small because in the experiments we are at 0.34. Okay, you also notice that when we are unstable, there is a threshold. It's just because the forcing amplitude must compensate for the viscous diffusion. And that can be found by simply doing a local analysis, a WKB type analysis of the flow. And we find a growth rate that goes like this. So the growth rate is linearly varying with the amplitude of the ellipsoidal shape of the container times the amplitude of the forcing and minus the viscous dissipation in here. The same is true for tides, and we have worked a lot on showing also that the same mechanism can still apply when your background flow is convecting or is stably stratified or when there is a magnetic field in the ambient, and so on. So it's a very generic and very efficient mechanism to generate instabilities. So are they present in planets? That's the next question. And as always, what we can do in the lab in terms of Ekman number is here, and where the planets are at Ekman number 10 orders of magnitude away. For the instability, all that does matter is the ratio here between the forcing amplitude and the Ekman number. So what we do in the experiment is that we have a larger forcing so that we can compensate for the fact that we have a large Ekman number. But we can extrapolate our scaling law for the growth rate and for the threshold down to a typical value for planets. So we have here some disappointing results, for instance, for Ganymede and Mercury, which seems to be below the threshold, but we are not yet given up, and we have additional things to look at. But we also have some very nice situation. For instance, the moon. So the moon had a dynamo between 3 and 4 billion years ago, and that cannot be explained by convection. So those two models try to explain the past dynamo of the moon using either precession or libration or tides. This nice model for Mars here by Jafar Arkani Ahmed, he imagines that, so again, Mars had a dynamo in the past and it does not have a dynamo today. So Jafar says that in the past, Mars had a moon which progressively circles around and comes closer and closer to Mars until it crashes, it reaches the Roche limit and crashes. But during the time where it was close to Mars, he was capable of exciting big tides, and so a dynamo in Mars. And finally, this precession or tide dynamo by Andrew, it's to explain the early Earth. Back in the past, the moon was closer to the Earth, and the Earth was precessing faster, and we had stronger tides, meaning that the Earth, which is just at the threshold today, was clearly above the threshold. And again, the past magnetic field of the Earth, so 4 billion years ago, could be explained by a dynamo of mechanical type. Okay, but you might have noticed that all my experiments, I have not said it, but everything was done with water because it's too difficult to use liquid metal. So I don't have actually a dynamo. All that I've shown you are turbulent flows. So to look at dynamo's effect, we use numerical simulation. But here it's very tricky because what we need to excite those instabilities are three-axial container, ellipsoids whose three directions are different. So we cannot use classical MHD spherical model because they will simply not excite our instabilities. So there have been only very few numerical studies of dynamo driven by this mechanism. Actually, I think there are 9 papers up to today. And those papers are either looking at laminar dynamo, because they use finite elements, for instance, and they cannot reach a very low Ekman number. So they look only at the laminar flow, meaning it's a first state, which is not the interesting one for planetary application. Other models, like for instance the work by David Sebron, use tricks. So they use spherical models in which they had body forces to try to mimic the real excitation. This is also interesting, but it remains, again, limited to very laminar cases. And finally, there have been some turbulent dynamo for precession, but only in the case of sphere. And in the case of sphere, there is a precession instability, but it is only driven by viscous coupling. Why, when you look at precession in a three-axial ellipsoid, you will have also topographic coupling, topographic driving of your instability. So precession in a sphere is much less efficient at driving turbulence than precession in a triaxial ellipsoid. So we need dynamo driven by turbulent flow in non-axis symmetric domain. So that's what we have tried to do. And to do that, we have used a model, a numerical method, NEC 5000, that you might know, which is based on spectral elements. So what we do is we have here an ellipsoidal container which is conducting, where we solve both the Navier-Stokes and the induction equation. And since it is a local model, it's very difficult to have, we need local boundary condition for the magnetic field also. So we cannot simply, as is classically done in numerical simulation in sphere, connect our field with an outside non-conducting domain. What we have to do here, and also NEC 5000 is not well shaped to have nice, to have ideal boundary condition for the magnetic field. So what we do is that we put our ellipsoid in a larger domain which has a poorly conducting value, and so we have two additional parameters: the aspect ratio of the two domains and the diffusivity ratio of the two domains. Okay, so we have made convergence tests on this. And so we work in the frame of reference where the container is fixed because it has an ellipsoidal shape, so we don't want it to move. Then we add the Coriolis and Poincaré force, and we solve for kinematic dynamo up to now. So again, we solve for the Navier-Stokes equation only in the inner domain. The outer domain is motionless, but it's conducting with a high diffusivity and magnetic diffusivity. Okay, so how do we do it? So first we run only the hydrodynamic part of the code that you see here. So this is again the libration case, work of Benjamin Favier. And once the kinetic energy reaches a quasi-stationary steady state, we introduce a seed dynamo and we look at the growth or not of the magnetic field depending on the magnetic Prandtl number. So here are some results for all the cases, and the good news is that libration, precession, and tides all are dynamo capable. So we have done some systematics. For libration and tides, we have chosen our best case from experiments and from numerical simulation. And we have changed the magnetic Prandtl number, measure the growth rate, and we find a critical magnetic Prandtl number of around 2 for libration, and for tides of around 0.5 here. Okay, so it's not great for planetary application, but again, we are at Ekman number 2, 10 to the minus 4, and at least it's not that worse than what people with convective dynamo do. Maybe the most interesting case is for precession. So in that case, there were already dynamo simulation in the sphere. So what we have done is that we have taken such a case with a magnetic Prandtl number of 1, and we have changed the ellipticity of our container in the plane, in the equatorial plane. So here we recover previous results. It gives us a good benchmark when the ellipticity is 0, meaning that we have a sphere. And the larger the ellipticity, the stronger is the dynamo, which is also a good news for planetary application, because up to now people were saying when we go to low Ekman number in the sphere, the viscous coupling that generates the precession instability disappear, and so it's impossible to get a precession dynamo in planetary limits. It is not true, again, in a triaxial ellipsoid where you will keep this topographic coupling. Okay, so that's where we are today. So we have run the first dynamo, including the Lorentz force, but it's very preliminary results. We have here 2 cases where you see that we have the exponential growth of the magnetic energy and then some saturation. So we are happy with that. It's not, from a geophysical point of view, it's not very interesting now because we have a small-scale dynamo, as you might see here, with not a lot of energy. So the magnetic energy is about 10% of the kinetic energy. So, but again, it's only one case for now, and we know, so the pessimistic view is all the dynamo will be like that, but the optimistic view is from a paper of Moffat in the 70s, who look at the dynamo generated by small-scale inertial waves, and he gets, in some cases, a large-scale flow from small-scale inertial wave turbulence. So my key point is that we have a huge parameter space to explore. Up to now, there have been only 10 papers about this subject, so anyone who wants to start working on this, I would be more than happy to share the work. Then, also, an interesting point is that we have a tendency to study each phenomena separately. So some people look at convection and they want only convective dynamos, some people look at precession, some people look, and so on. In nature, everything takes place at the same time. So, for instance, the Earth is both tidal and tidally distorted and precessing. So the mechanism may collaborate and some interesting things might happen. The same is true for convection. The Earth is both precessing and convecting. And there is this very nice paper by Wei, who shows that he shows 3 cases. A case which is stable when it is precessing only, which is dynamo stable when it is precessing only, dynamo stable when it is convecting only, but when you put both precession and convection, it becomes dynamo unstable. So that's also a very interesting thing. It's that the difference effects, they are not opposite, but they might collaborate. And finally, is it possible to make MHD experiments? So I'm not crazy, but somehow. And we have already heard about this very, very nice experiment that is coming in short time in Dresden, which is precessing. So it's in a cylinder, but the dynamics will be about the same. And I stop here. Thank you.
Thanks, Michael. Question over there?
I have a question about the energetics. Presumably if you're with tides sort of driving waves in the interior that are breaking or then inducing a dynamo, there'll be dissipation associated with that. And there's constraints on the total dissipation that can happen in the Earth just based on the moon's location. If the dissipation were too large, then given where the moon is now, the moon would have been close to the Earth, not 4 billion years ago, but maybe less. Okay. So I was wondering if the numbers work out. The Q of the Earth it has to be more than a few tens or something.
Yeah. So in our experiments, we have a motor that drives the system. So in a real situation, planets slow down and they go away when you dissipate energy because of your instability, of course. The main point is that the energy that is available is the energy that sustains the waves. As long as you have waves, the mechanism is possible. So you have a huge amount of energy. That's the first calculation I made at the beginning. So that's the first part of my answer. Second part of my answer about the dissipation itself. The only place where we have measurements is for the moon, because we can measure the distance between the Earth and the moon. And so if you take that number, first it shows that it can only be explained if the core of the moon is turbulent, which is surprising, because we would expect the core of the moon to be still today, even to be fully solidified, but it's not the case. So the core of the moon has to be turbulent today, which is surprising. And then the number works well. That's what the calculation I did in the Andro et al. Paper in 2017. Even today, we have enough energy when you compare this with the Earth.
The moon is moving faster from the Earth now than is the case over solar system history. So the dissipation that's happening right now inside the Earth
right now is enough,
much
and in
higher
the past
than
it was
historical average.
Even better.
No. Right now the dissipation is greater than, the Q of the Earth right now is like 10 or something. So if you take the dissipation of the Earth now and integrate backwards the evolution of the moon would have been close to the Earth like 1 or 2 billion years ago. So that doesn't work.
It was closer, meaning that you had more energy put into your core. Another way to say it is that today we are missing between 0.1 and 1 terawatts when you look at the Earth engine, between what is coming in from the tide and so on, what is dissipated in the ocean and so on. So this 1 terawatt that is missing could well go into the core and sustain dynamo. And this 1 terawatt is enough to sustain the present-day magnetic field. So the numbers are working well. At least they are not completely crazy.
Hi. So I saw some, I'm not an expert, I remember some models like U-Fanglins and recently Nathaniel showed something. They usually find with precession, they usually find something that has 3 columns, both in the magnetic field and in the flow. You see anything like that? And
that will be my second talk tomorrow.
Oh, cool.
Okay. So it's a nonlinear evolution of the instability. I will show you that tomorrow.
It would seem that Europa would be a superb system to try to test some of these ideas, and I was wondering if you'd thought of applying your models to that.
Europa?
Europa, yes. Undersea ocean, magnetic field. That's our reason for arguing that Europa has an under ice ocean. The fact that it has a magnetic field associated with it, that means there has to be a conducting fluid, and we know very strong tidal stresses are involved. So I just wondered if you'd thought about that.
That's a good idea, but Europa does not have a dynamo, right? But it has
it has magnetic field.
It has magnetic field, but it is inducted from the Jupiter, no?
That's not clear.
That's not clear, okay. Another thing that I wanted to say about that is that I talk about core mostly, but all that I show you here also works well for subsurface ocean, of course. And one case that is very interesting also today is Enceladus, where we have an anomalously high dissipation at the pole. And maybe turbulence generated by such type of instability might contribute to explain Enceladus' anomalously high Europa, yes, that's also. I thought it was clear it had no dynamo at all.
This issue about whether you should be optimistic or pessimistic because you have a small-scale dynamo, I think you should be optimistic because you're at far too high PM in order to get a dynamo in the first place. So as you reduce PM, the ratio of small-scale to large-scale should go in your favor.
Mm-hmm. So with DNS, we will not be able to test that at all.
Okay.
What we plan to do now is to use the local method that we show tomorrow to look at how wave turbulence might or might not generate a large-scale magnetic field. That's something that we have just started right now. And I hope we can be optimistic, of course.
Let's come back at 3:15. Thank all the speakers.